Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, Episode 4 of 15. You might know exactly where a star is tonight, but without proper motion and Earth's velocity corrections, your telescope will be pointing at empty space next decade. This is where we go beyond RA and DE, three-dimensional tracking, and velocities. By default, coordinates map a flat position on the sky using angles. To model a physical system, like a binary star system, you need the actual physical space between the components. Many people try to compute a three-dimensional separation using just right ascension and declination. That does not work. To use the three-dimensional separation method, you must provide a distance parameter when creating the coordinate object. You pass a distance value with a physical unit, like parsecs, alongside your angular coordinates. Once both objects contain this distance data, you call the three-dimensional separation method on the first coordinate, passing the second coordinate as an argument. Astropy returns the direct physical line between them in three-dimensional space, automatically handling the background trigonometry. Now, those objects are not static. To model their movement over time, you attach velocity data directly to the coordinate object upon creation. You do this by passing proper motion parameters. Specifically, you provide proper motion in right ascension and proper motion in declination. These take angular units per time, like milliarcseconds per year. You also provide a radial velocity parameter, which takes a physical speed, like kilometers per second. When you bundle these together, the coordinate object becomes a full phase space vector. It holds the object's current location and the exact vector of where it is going. Here is the key insight. Your telescope is also moving through space. Earth rotates on its axis and orbits the sun. If you measure the radial velocity of a star from the ground, your raw measurement is contaminated by Earth's own speed at that exact moment. To share your data with other astronomers, you must strip away Earth's motion. You shift your reference point to a stable frame, usually the center of mass of the solar system. This is called the barycentric radial velocity correction. To calculate this correction in Astropy, you need to define where the observer is using an Earth location object. You create this by passing the exact longitude, latitude, and elevation of your instrument. Alternatively, you can pull an established site directly from Astropy's built-in site registry by querying a known name like the Keck Observatory. Next, you need the exact time the observation took place. With your location and time ready, you call the radial velocity correction method directly on your target's coordinate object. You pass it the observation time and your Earth location. Astropy computes the velocity vector of the Keck Observatory at that specific millisecond relative to the target and returns the velocity offset. You add this correction value to your raw measured radial velocity. The result is a clean, standardized measurement referenced to the solar system barycenter. The single most useful takeaway here is that a coordinate is not just a fixed point on a map, it is a full kinematic model that holds the target's position, its trajectory, and the geometry needed to correct for your own motion. Thanks for listening. Take care, everyone.